So perhaps you're okay with the basic concepts of the math and all of that stuff that we will want to be using in the node editor from time to time for certain things here and there. But, of course, there is a big difference between just getting the basic concepts and, working with the different equations and formulas for this, that and the other. Here's the thing though, all you really need is to understand the concepts and, I'll admit, have a basic understanding of how things are notated. And you may think that therefore trying to invent or dream up your own structures to use in Nodal is still going to be a bit difficult. Now first of all, knowing the concepts will help you. Just start wiring concepts together. Stuff will emerge and you can sort of hammer out the fine details bit by bit. But in a lot of cases, the sort of structures that you are going to want are things that are already known, have already been discovered and whatnot. And so as long as you have a basic understanding of the concepts and principles at work, you can easily go looking for little chunks of math that already do what you're wanting to do. Of course, again, you might think to yourself, well, even if I get the basic concept, I'm still not completely happy about dealing with the formulas and equations and whatnot. You will not have to. Or rather, and this is the interesting thing, what you will need is not a good knowledge and ability to work with the math itself, but a good knowledge of LightWave and the ability to work with LightWave. Not really knowing what various formulas mean is kind of okay. Not knowing how LightWave will interpret certain things or how it works will give you problems, because you will be unable to give LightWave the information in the correct way. So here we go with a little demonstration that will show just how easy it is to take something without really knowing about it and get a result out of it, so long as we keep LightWave's way of working in mind. Okay, so what I have here, little chain of 3 bones, and we're going to make an IK solver. Now of course, I do know that we already have an IK solver in LightWave, and so this isn't the sort of thing that you would commonly have much call to do. But there will be lots of tools that are called upon. But let us imagine for a moment that LightWave were lacking this IK. This is a great thing that Nodal can do for us, help us to build functionality that our package is otherwise missing. Righto, so goal item in place. Now, first thing we need to do is try and get the picture in our head. We're trying to create an IK solver, so as when we move this goal here, the arm will respond, or the leg, or whatever this might happen to be. Well, what is an arm or a leg when it's working on IK? Well, basically, it's a triangle, right? You've got one side, the upper arm, another side, the forearm, to the wrist point, and then between the wrist and the shoulder is the third side, which is the distance shoulder to goal, or root to goal, rather. So it's a triangle. So, with our basic knowledge of math principles, I kinda get the idea that maybe I can figure out this arm based on the math of triangles, which is trigonometry. A little more thought, and I should realise that obviously the length of the upper arm, the length of the forearm, and the distance here between the root and the goal are obviously known. These are the sides of the triangle, they're known distances. What I need to find out is the angles. Those are the unknowns. Having made myself familiar with such things, and even if I haven't, with a little bit of Googling, find angles in triangle, it quickly becomes apparent that what I need is the law of cosines. Now I look, and there's a whole bunch of stuff here, which looks terribly confusing, but I see this lovely little picture over here, and this is sort of showing me what I've got. I've got my sides and I've got my angles. If we scroll down and just have a little light read, we find an example problem right here, where we have an unknown angle, which we see in the picture above is being denoted here as gamma. Here's a little formula that contains gamma. Gamma is equal to this thing. That's this angle. So if I'm going with the thought that this point here is my shoulder, this point over here is my wrist, then A is my forearm, B is my upper arm, and the angle here, gamma, is the elbow. So there I've got a formula for it. Do I have to be able to do this formula or know anything about it? No, I just have to be able to copy it. So, into LightWave, we're getting the angle inside here, so that means it's going to be rotating the forearm at the elbow there. So we'll start with this guy and give him a nodal motion. So where do we begin? Well, the rotation input here is the angle setting. So effectively, this is gamma. So here's my little thing. Right, well, we'll start in the brackets because there's this arc cos that does arc cos on the contents of these brackets. So let's figure those out first. A squared, B squared, C squared. Right, that's easy enough. So if A is our forearm, this side here, then it's the length from the elbow to the wrist. I could use a constant in here to just enter that value, but what I'm going to do instead is use some item info and turn to DP here so as I can get the bone info. So first of all, let me rename this. This is going to be our A. The object is the bone's null, and the bone is the hand, not the forearm, because I'm wanting the length, and that is given by the hand's Z position. So what I'm going to use here is one of TrueArt's split vector nodes, simply for clarity, and there's our Z position. So this scalar is length A. I'm going to change those names a bit so as that becomes A, and that's clearly referencing the hand there. Okay, we want B. B is the length of this upper arm bone, so we basically want the exact same thing here, except I'm going to change this from hand to forearm, which of course is length B. So there's my A and B. Now C, that's the distance shoulder to goal. So we're just going to work with the Z-axis for now because it's nice and straightforward. So I get a regular item info here, which I of course set to be the goal, and again I can grab it Z. These need to be squared, so let's get a scalar multiply, and we can just do Z times Z. Of course doing that for the other two as well. So now we have A squared, B squared, and C squared. What was the formula again? A squared plus B squared minus C squared divided by 2AB. So we take an add and a subtract, and that gives us A squared plus B squared minus C squared. Okay, super. So we can just give that a little name there to help us remember which bit it is. So that is then divided by 2AB. That's 2 times A times B. So another multiply. There's A times B here, and we want two of them. So another multiply node. We connect that into there, and of course multiply by 2. Little rename, that's our 2AB. So it's this guy divided by this one. So a divide node comes in. This divided by that. So that gives us the result of everything in the brackets, and we want arc cos, or inverse cosine. We grab our handy little arc cos node then, plug that in, and bingo, there's our result. All I have to do now is get a make vector node. We're wanting to rotate on the heading here. So we plug that into the X, vector into rotation, and there we go. We have solved the angle between these two bones here. Now what we need to do is find the appropriate angle for this bone. So we could continue on and actually solve it with the cosines again, but if we look for a nice handy formula to tell us this alpha, capital A, angle down here, which is of course the shoulder one that we're now going after, there doesn't seem to be an easy listing for it. However, if we do know our basics, we'll know that we can also turn to the law of sines, which works when we know at least one of the angles involved, which we now do, this elbow gamma angle. So I'm going to jump there and look for an answer. Oh, and here we go, straight away, this law of sines. Now we can flip these guys about to make them the right way to find A, but if we just look here, we see that somebody's already shown an example of it. So they've got this angle A here, and side A opposite it. An example of A being 20 long, C 24 long, and C angle 40 degrees. Well, we already know this C angle, so that's handy. We know the length of the sides, and they're showing here, therefore, that A is equal to the arc sine of 20, so that's the length of A, times the sine of this angle here, divided by the length C here. So once again, pop the nodal motion on our upper arm bone there, and let's see what we need. Well, I know that I need to get the angle of the arm here, so I'm going to grab another bone info for the forearm, and of course I can get its rotation. Use a split vector, grab its heading, and so this output is now that angle C, gamma from the previous page. Let's call it capital C there. So let's look again. So 40, that's our C, so we want to sine it and multiply it by the length of A. Sine it, that's easy. We just grab the sine node here, There we go. That's the sine of that angle now. We're wanting length A, which was the forearm length, so the hand Z position, so we get the hand, and there we go. Its Z position is little a, so we multiply length A by the sine of angle C, so that's A sin C. Then we want to divide that total by the length of side C. So that's the distance to the goal. So regular item info there to grab the goal item. Here we go, our length C coming out there. And we can divide our one value by the other. Super. And we see that once again we need an inverse function, arcsine. So we grab the arcsine node, plug that into it, make vector, again for the heading axis, and plug it in. Okay, and bingo, we see that it's gone completely wrong. If I move my goal here, well, something's happening. It's looking a bit bizarre, but obviously there is action. So we are getting a drive. So what have I done wrong? Have I got all of this wrong because I basically just copied what was written here without understanding it? Well, no is the answer. I've got it quite right. You know, I've got all of these terms just copied out one by one, plugged into each other. We can go back, read through it, double check it, grab a spy, check the values that are coming out of places to make sure that it's happening correctly. These things aren't going to be wrong. So what this tells me is that what I have missed is the way LightWave itself works and interprets everything. Let's just kill those nodal motions momentarily. Now, we do want the forearm to bend this way at the elbow, okay? That's positive. For the forearm to do that, we need the upper arm to be bending back this way, which is negative. Of course, however, the network is just delivering a positive value. So we need to flip that. Easily done with a sine node. And no, we're not talking about sine, we're talking about the plus minus switch sign. I know it is a bit of a pain them having the same name, but there you go. If I take the result of my whole trig thing here, plug it into that, goes from positive to negative, plug that into X. There we go. Our upper arm is correct. But clearly something isn't so correct, because that's still obviously not working. Once again, it's just forgetting to think about things in terms of LightWave. When we solved for the forearm, we solved for this internal angle here, right? That's the value that the forearm has been set to, what we calculated the internal angle of this triangle ought to be. But our forearm, when it's at 0, comes straight out from the parent like this. We're not trying to find the internal angle to turn it. We're trying to turn it until that angle exists in between these two bones. So the solve I have for this guy is wrong. I want to get the amount of turn he reaches to create that internal angle. Well, that's pretty simple, because when he's out straight, the internal angle is a full 180 degrees. So the amount he needs to turn is 180 minus whatever we found for the internal angle. That'll give this little bit of external angle there. So we go back into his node motion. We want to find the angle, not the sine, cosine 0 to 1 value. And so of course that angle is coming out of arc cos here. So I can take constant angle, a scalar, subtract, enter 180 degrees minus whatever this result was, and plug that in. Bingo. And now, when I move the null on Z, our thing works. Except we'll notice that I pull it a bit too far out and it sort of vanishes. If I pull it too far in, it vanishes again. So something's not entirely right. We can worry about that in a moment, because we'll also notice that if I pull it around on X, then it's not responding at all. So it's just sort of this linear IK solver with a little bit of unusual magical vanishing behavior there. Of course, this is the point where the good old Wikipedia sort of runs out of usefulness, because none of this is really telling me how to take into account the extra axis and everything else of the goal object. But that's not the important thing. The important thing with this demonstration is the fact that so long as you know the basic interface of the node editor, what nodes you've got, how to plug stuff up. You can just go and look up formulas for things and copy them into the node editor, making any LightWave specific changes that are needed along the way to account for parenting or rotation order or whatnot. And you will be able to build stuff without essentially having to know how to do it by yourself, simply by copying. We'll also notice something else cool that's come through on here. Because I've taken the positions of the bones directly into these networks rather than just entering their values somehow, it means that when I move things on Z, the IK can update to accommodate the altered position, which means I've effectively got stretchy IK out of this solver as well, which is pretty cool. But what I'm going to do now is just finish this whole thing off anyway, just to show you. Obviously it's not the purpose of this tutorial, and some of the stuff won't make sense until you've been through other videos in this series. But reflect back on this later. It's all good stuff to know and examples to see and things to think about. So let's take a look at the X position of this goal null. Basically, whenever this moves somewhere on X, you can draw an angle between it and the root of the chain there, the shoulder. Obviously all that needs to happen is that angle needs to be added on to the one that it's already turning. Go into the node motion for the upper arm here. Of course we've got the goal item info there. I'm going to get another item info here, which is just going to be the bones null item there. I'm going to subtract the position of one from the position of the other, use that as a direction to create a rotation, get just the heading component of that rotation, and then simply get an add to add it on to the existing rotation we've already got. And there we go. Now the arm responds to the X as well. But what we notice is that the wrist is no longer meeting it. The reason, of course, is because of length C, distance between the shoulder point and the goal item. Because I've moved on X, this is different. We've only been taking account of the Z. So what I need is the distance between them, and to replace my existing C with that. Well, here's my C value in this network, so I may as well start here. Get a vector distance node, and I can take the position from that bones null to the goal item, or, well, either way round, makes no difference. And this is now my new C, so I plug that in where C was. I can get rid of that thing. It's made a change, and it's a little better, but obviously we still need to adjust for the forearm as well, so I go back into there. Here is its C. So remember we had C squared going on over here. So that's the goal item info. I get an additional info therefore that I set to the bones null parent object. Distance again between the two of them. And there's my new value for C in here. And as we can see, it now works just lovely. You can go all the way around there. And it works fantastic. And of course if I grab the root of these bones and move that, then it also works. So it's a proper IK solution in that way. So that's one thing I've fixed. So how's about this other behavior where it just seems to disappear at certain points? The bones themselves, literally, they are just vanishing. That's a pretty peculiar thing to have going on, right? Here's the reason why it's happening. It is because, of course, sine, cosine results vary between 0 and 1 and so on. And we have divide nodes in here. It's possible in some poses to wind up with numbers coming out of the network that wind up dividing by 0, the answer to which is infinity. And infinity to computers is just a complete nonsense number. It's uncomputable. And so what you get is just an error. If I grab at this point the good old input spy and we have a look at what's coming out of our arc costs here, we can see it's -1 hashtag ind, which is LightWave's way of saying indeterminable. You have created a number that cannot be computed, at least not by a regular computer. And that is why everything has vanished, because the rotations have effectively become infinite, and so LightWave's gone, no thanks. If we pick the arm there, look, its rotation handle is still showing, it's somehow still there, but we can see again down here 1.#r degrees. Just nonsense for a value. Same again for the forearm, -1.#j degrees. Brilliant. There is a simple fix though, and that's to start clamping things to stop them going awry. So I can chuck a math scalar clamp node in here, Now, I could fit it inside the network somewhere so as the numbers behave themselves, but quite frankly, the simplest place for me to chuck it is just going to be at the end result of everything. So in comes my input from the subtract. I'm going to say that you can go no lower than 0.0001, so that prevents that dropping to 0, which is the point at which it all goes nuts. And your high can, well, that can be anything, quite frankly, doesn't matter. I pump that result back in, and our bones reappear. You see that my heading rotation is now 0.01. It cannot go any lower than that. And we see as we move our null, our IK just terminates and snaps. And when we come down too close, it just snaps out straight, which is quite a common thing that we might have seen in IK solvers if we've been playing with them before and wondering why we get these weird behaviours. It's intrinsic in the math, you see. And here's another such behaviour, which is the snappy poppy IK. You notice as I come closer to straight, sooner or later, it just pops. See? You get the little IK snap at the end there, where you don't get this perfectly smooth thing. Remember the old poppy knees and poppy elbows with IK? Again, it's part of the intrinsic nature of the math. You remember, of course, that sine and cosine were these nice smooth waves. That's terribly badly drawn, but still, against a graph axis here, which represented, so much angle and whatnot. But because of this slow takeoff, you see, when you're at incredibly shallow angles, the sine value becomes ever more and more indeterminate. Of course, it's possible to calculate as shallow an angle as you like, just so long as your software or computer or calculator is kicking out enough decimal places. Most 3D softwares will not go to many, many, many decimal places. They'll only go to 3 or 4, which is why you always get that snap in IK. The snap that you see is this curve bottoming out or topping out, whichever side of the sine you happen to be on, the 0 or the 1. So there we go. I know we've drifted off on a little bit of a side there as I've explained the fixing of this IK chain and the clamping and the behaviour of sine causing the snapping. Maybe it's given you a little bit of further insight into IK that you never knew about, so I'm sure that's worth knowing. But the primary point of this video has been to demonstrate that as long as you get the basic ideas of what these formulas or equations are talking about, you don't need to know the formulas, you don't need to understand how to process them or do the numbers by yourself. All you have to be able to do is look up the formula somewhere and copy it. And you can create these mathematical machines, for want of a better word, without having to actually know the math. You're just grabbing pieces of math and plugging them together. The computer is doing all of the actual number crunching. We don't have to worry about that. So if you're approaching this as an artist, don't try to look for the numerical solution or the mathematical solution. Just think in the most basic terms, like here, I wanted IK, which is a triangle. So I looked up triangles, found the appropriate formula, and just copied it. Look for the shapes, look for the motions, look for the curvatures that you're wanting to create. Read a bit about math so as you know which areas of math talk about these different kinds of shape, and then just turn to them as you need them and grab the stuff that you need and just plug it in. That really is all there is to it. So I hope that this little step-by-step of doing this has introduced you to a process or a technique that you will find helpful in creating the kind of stuff you need when you need it, without having to know all of the math that gets used in it, and of course without having to just think it up by yourself. So there we go. The best thing you can do at this point is to start digging round, have a look at some of the things that happen in 3D, try and identify the basic shapes, see if you can dig around online a bit and identify fields or formulas that equate to those shapes and describe them. It's hard to find a good technique that will work for everyone who is much more on the artist side of things. But if you give this a go, I am sure that everyone can at least get something out of it. And of course, the more you practice, the easier and the better that will become.